Assalamualaikum and a very good afternoon to everyone. Okay, so today I will present lecture 5, which is the phase equilibria. Okay, so this is our objective for this lecture. The first is to present the general calculation procedure for VLE by an extension of modified Rock's law, and to formulate general calculation procedure for VLE by equation of state, and to inspect phase equilibria with consideration given in separate sections to liquid, vapor, liquid, solid liquid, and solid vapor, and introduce adsorptions and osmotic equilibria. Okay, right. So for the modified Rod's law, okay, right. So we have the activity coefficients, right, to account for liquid phase non-ideality. Okay, right. So everybody have seen it here. This is for the vapor, viscosity vapor, Y, and activity coefficients here, okay, and P. And then for liquid, we have X, gamma here, and F for viscosity. Okay. Okay, right. So this is the viscosity coefficient, and this is activity coefficients. Okay, right? So they require these two expression to be equal. Okay, right? Because it is in an equilibrium. Okay, right? So this is in the vapor phase, and then it's in the liquid phase, and then we can rewrite this into this form here, where the capital Phi here is this equation. Okay, guys. Okay. Okay, right? Because the fees for the vapor phase and the gamma and viscosity are liquid phase properties. Okay. Okay, right. So this capital fees I is also equal to this fee at a specific species to is saturated. Okay, right. So this is I think you guys remember here. This is in solution, right? Okay. So and then in the Rath's law, when phi equal to gamma equal to 1, then modified rho, it become a modified rho, right? When delta phi is equal to 1 here, okay? So to find P saturated, then we can use Anton equation here, right? A plus B plus T plus C, where all these values, right, you can find it in the appendix, okay? And then for the two-term viral expansion, we can use the equation here. I don't need to expand it further. Okay, right? So the V, we have this, this is the two-viral equation, VII, get out all this summation here, where gamma Ji equal to this and gamma Jk equal to this. Okay, right. So the phi saturated equal to the exponent of VIR over here, and then we can find what is the phi for the specific species. Okay, right, using this equation here. So for a binary system of species 1 and 2, we get this equation here. Okay, right, V1 and V2. Okay, right. Okay. And then for the activity coefficients, it can be evaluated using the GE function as discussed in the previous lecture. Okay, right. So which is a GERT is a function of x1, x2 until xn minus 1, where the t is constant. Okay, so phi is a function of TPY into yn. Okay, and then this activity coefficients is a function of this, and Pi saturated is a function of temperature. Okay, right. So from these, then we can use the bubble P calculation to yield 1. Okay, right, in the previous lecture, and then they also given you how to calculate that, and also there's a way to program it in the appendix. So equation 40 can be solved for this. Okay, right? So we'll get this equation here, right? Yi for vapor and for the liquid phase. Okay, Xi. Okay, in this form. Okay, right. So if we know that summation of all the vapor fractions should be equal to 1, and for the liquid fraction should be equal to 1, and then we get this equation here, then we can find what is the pressure is. Okay, so it is this. Okay, right. So P will the summation of I, all these values here, parameters. Okay, right. It's the same also for this. Okay, right. This is the inverse. Okay, this for liquid and this is for the vapor. Okay, right. So this is the procedure, we can find the pressure, okay, right? This is a block diagram for a calculation bubble pressure P. Okay, right? We get all the parameters here. We evaluate P set and this, and calculate for P using equation 14.10. We calculate the YI, and then this and evaluate the phi, okay, right? So, and then we calculate P again using the equation 14.10, and then we need to find the difference of the pressure, okay, right? So, if the change in pressure is less than the epsilon. Okay, epsilon here indicate a tolerance, okay, right? What you set the tolerance, how big the differences you want to have it. If you want to be, the smaller you get, the more iteration you need to do. Okay, right? But if the delta P is within the tolerance, okay, right? So it's acceptable, then we can find what P is. Okay. This is the block diagram for the calculation of dew point, okay, right? Pressure. Okay? It's the same thing. We got all this data here. We evaluate a phi, capital P, okay, right? And then we normalize the value, evaluate gamma 1, okay, right? Is this gamma 1 is smaller than the epsilon, okay? So it's something, right? The differences, okay, right? uh, of the gamma just now, right? Is it acceptable? Then it's yes, and then we can calculate for pressure, and then with that we compare it to the uh, the the calculated pressure here. Okay, right? So is it equivalent? Is less than the tolerance that we set. If it does, then we can accept the pressure. If not, then we repeat this procedure again. So guys, you can see it here. Then you need to write the program to calculate this. Okay, you can use any program you want, MATLAB or whatever, but Excel also will be visible if you know how to program that. Okay. Okay, for in bubble point and dew point calculation, temperature is given, so it's very easy, okay, right? But not in the case when we calculate for bubble point at temperature and the dew point temperature, okay, right? So this is require more iterations, okay, right? So for this, okay, right, it depends on whether the xi or yi is known, okay, right? So T can be in this form or this form here. This is for the vapor, this is for the liquid. And then we use the Anton equation again, okay, right? To find what the T saturated. And from this, okay, right, we use this equation to find Pj saturated, okay, the one that we fix, okay, right? And then J also here, okay, right? Okay, right? And then T, and then for this, for calculation of bubble point, we find all the data in here, and then we calculate, evaluate what P is, calculate Y, capital V, P, and T, and then is it delta T is less than the tolerance that we set. So if it's yes, then get the T. If not, then we repeat the calculation again. Okay, with the new T. Okay, right? So over here we got the T, isn't it? And this is the set T or gassing T. So we got this, and then we use that T again and calculate. Okay, right. So this is for the dew point. It's the same thing. We need to calculate all the parameters here, and then we import the P saturated, and then also the capital V, and then we calculate Xi and normalize the value and evaluate a gamma 1. Okay, right. If this is within our tolerance, then it's okay. Okay, right. Proceed to find the P saturated. If not, and then we'll repeat it again. And then this calculation, it will be accepted, okay, within the tolerance and the P, and then we check it for the change in temperature. Is it within our tolerance also? If it's yes, then accept. If not, then we repeat the whole process. Okay, now for the flash calculations, okay, right, in the previous lectures, that we can use YI using this equation here. Okay, right? So this is the ni, okay, ni, and then XI is YI over KI. Okay, we have done it earlier, even in the quiz. Okay, right? So from here that we can find what is XI. Okay, right? The liquid fractions. Okay, ZI over this value here, and then we can find the different, okay, right? All over the sum, subtract unity from this sum, the different Fy is 0, okay, right? So we find the different of Fy here, okay, right? This minus 1 is equal to 0, and the same also for Fx. So for this, okay, right, F can be in this function here, okay, right? And it's equal to 0, okay, right? Because Fy minus Fx is equal to F. Okay, right? So it's the same, the differences, okay, right? Because it is in equilibriums. And then the f over this, okay, we find this and then we can rewrite it into this form here in Newton's method, okay. I will not talk in Newton methods. I think that this have been covered in your mathematics class, but it's okay, you just accept, right? And then toward the end, okay, right, to the end, k can be evaluated into this form, which is yi over xi. Can you guys remember, or can be written into this form, okay, right? So, and the k values contain all the thermodynamic information are related in a complex way to TP1 and xi. Okay, because solution for this, the TP flex calculation inevitably require iteration. Yes, definitely, right? Because we need we cannot because it varies, right, the PNT. Okay, so this is the way how to calculate the knee, okay, right? Okay, right? So first we did TMP and the constraint, okay, right? And then we calculate the dew point calculation with this, and then after that we calculate the bubble point, and if the P the dew point and P less than the bubble point, then is it no, then stop, means that it's not possible to achieve that. If yes, then we estimate gamma, capital phi, and mi here, okay, right? And then we evaluate K and blah and all of other things, right? And then we find the change in ni here, okay, right? And change in x and in y, is it less than the tolerance? If yes, then we can accept these values. Okay, if not, then we repeat it again. Okay, right. A gamma phi formulation of VLE, solid 1 and solvent 2 systems. Okay. So if you still remember that we have the Henry's law, right? So Henry's constant is the limit of xi equal to 0 for this ratio here. Or in another term, this ratio can be estimated using this gamma 1 and viscosity 1, or in another form, if you guys still remember, Henry's law is this. Is it apply for infinite dilutions? Okay, right? Okay, so we use it for infinite dilutions. Okay, right? So we apply Henry's law. Okay, so Henry's law is there gamma 1 for infinite dilutions, right? And then viscosity 1, and then F1 is this equation here, okay, right? Uh, this is from the Raoult's law, okay, right? And then we know that F1 for liquid and vapor is equal to this, right? Y1 P, and then viscosity coefficient 1. Okay, now from this we can rewrite it again, and we find y1 equal to this equation and y2 is equal to that equations. Okay, so we can use these two equations. And then for a bubble, we know that y1 over 1 2 should be equal to 1 because it's the vapor fractions. And then for a bubble P calculation, we're binary system, and then we can use this equation here. Okay, that is equation 14.28. Okay, and then for GE, right? Okay, this is the excess. Remember, there's a x1, x2. Okay, now phi equal to 1 and p2 equal to 1 also. And then we can rewrite this. Okay, using this function here, it becomes this very long equation here, which include x1 and these numbers, and x2, p2 separated, right? And then y1 equal to this. Okay, this equation. Okay, now for comparison, if P saturated unknown, the formulation will be, okay, if the P1 saturated unknown, okay, right, so we can rewrite it into this form and y1 into this form here. Okay, right? And for the remaining, the power finding Henry's constant from the available VLE for equilibrium, I think we can use this equation here. And then, because we know that Henry constant is defined as the limit as x1 is going to 0, means that it's toward finite dilution. So the Henry's number can be into this form here. So the limiting value of y1, x1 can be found by plotting y1 over x1 versus x1 and extrapolating to 0. Okay, right? So it's the when it reach the axis. Okay, so In the previous section also, we know that the viscosity for the vapor should equal to the viscosity of the liquid here. So that's an alternative form. We can rewrite it into this y1 p v1v the viscosity coefficients equal to x1. Okay, this is the liquid fractions p and the viscosity coefficient in the liquid form for I or this equation here. Okay, right. Okay. Okay, so we continue our lecture. Okay, right. Now we'll be on the VLE for cubic equation of state. Okay, vapor pressure for a pure species. Okay, so in the lecture 2 that we have draw the Hughes shape. Is it nice to remember this? Okay, right. This is the critical temperature. Okay, right. So this all a compressed liquid. This all vapor. Okay, right. And this is saturated liquid line and saturated vapor line. In between here, there's a mixture. Okay. So if we plot down this graph here, okay, right. So when the pressure, the volume had been increased, we found that the pressure had been. Okay, right. If you notice the line in here, okay, right. If we increase the volume, okay, right, from liquid to vapor here, okay, right, this is a liquid point and saturated liquid point, the saturated vapor point. If we increase the volumes, okay, right, we will see that the pressure have dropped significantly until a certain volume again, the pressure increase, okay, right, and then increase and then it drop again until it reaches the saturated pressure line. Okay, right. In our thermal one, we assume that this to be in a straight line. Okay, but actually, if you guys can see here, okay, right, from this line, if you plotted that, okay, from R to S here, this is more on the liquid phase, okay, and then T to U, that is more on the vapor phase, and then S and T are the mixture, okay. So this is means that the effect this is more on the liquid. So what does it mean here? What happened here is that, as you increase the volume, the 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 fluid is still in liquid form. It have not been evaporated or changed into vapor. Okay, right? So that's why the pressure have been reduced. Okay, right? Because in the liquid and then there will be kind of like vacuum. So the pressure drops significantly. But as you increase again the pressure, okay, think of this way, a piston. Okay, very easy to piston. Okay, you put some liquid in there, okay, right? Because initially it is a compressed liquid here, okay, right? You put a liquid there and then it becomes saturated, and then you expand the piston. Okay, at the beginning, there's no vapor being formed; it's only liquid. So you will get a kind of a suction. Yeah? You pull it back. Okay, but when you pull it even further, okay, right? So we have the transitions of some of the liquid, right, in the piston start to evaporate into vapor, and then until a certain phases, there will be when you pull it again, there'll be more vapor than liquid until you expand the volume and toward the end, it's only vapor there. Okay, we can saturated vapor. So this is what the graph is all about. So you can see here, if you pull it, the piston, okay, that the liquid does not evaporate. Okay, that's still liquid form. So it create kind of like vacuum, right? Significant reduce in pressure. And over here, start the evaporation. So some vapor being produced, and then over here will be more vapor, and toward the end, it reach at W here, saturated vapor. Okay, VLE for cubic equation of state, vapor pressure for a pure species. Okay, so this is for the VLE calculation. Now we use the Slow, Fletchley, Kwong, KSRK equations, and also the Pang-Robinson equation. Okay, this is in our chapter 1 before. Okay, right? So we can use this equation here for we look for A, B, beta, and Q. Okay, right? And then this is all the values that you need to. This is for the liquid. And this is for the vapor. And for pure numbers, all these values is given in table 2.1 in page 98. Okay, but nowadays we don't use the table anymore because there are software to do that. In expert analysis, you can fill it up. They can look it for you. Okay, so before, but we do have the data that we can use this. Okay, so this is the equation for calculating vapor pressure. And normally we have this unknown, and it is the equation that can be used. Okay, for VLE from cubic equations of state, so this is for the mixed VLE. Okay, so vapor liquid equilibrium. So for the liquid, this is the equation we can use, and this for the vapor. And for the mixture, we can use this. Okay, where the mixture P is for L and V. So this is for both. Because it's a mixture. And then for the Q, we can use this equation here. Okay, right. For VLE from cubic equations of state mixed VLE. Okay, so as we done earlier, we have two kinds of equations that we can use. One is for the liquid and another one for the vapor. Okay, right. So if we plotted to the graph, is a change from liquid to vapor, we will get this equation here, where the solid line is from the liquid phase, and then the dash line is for the vapor phase. Okay, right? So in the saturated liquid is at the B here, okay, and the saturated vapor as the D here. You can see here. So normally we does not really mind, okay, right? From the change of liquid to vapor. Okay, right? So we assume it to be in a straight line, but it's actually what I have explained to you previously that okay, right? The change of a liquid to vapor it follow this trend here. Okay, right? Because there's no sudden change. Can I remember what I mentioned here? Over here, the liquid is still in liquid form. It have not been expanded or changed into vapor. So the pressure drop. But once it start to evaporate, then you can see some pressure increase because some of the liquid are written into vapor. And then this is the vapor phase here. Okay. Okay, that's what it means. Can I? And that we can do it further. Okay, for the mixing rules, there's no established stories, So what we can do is that we can assume it to be is a mix, okay, right. So it's a mix, quadratic mixing rules, So for parameter B, we can use this x1, B, and A in for that, right. And then this should be the same, and then O can be formed into a geometric means rule, right. So geometric means rule is a much better. It can tell you what directions it's going, okay. Okay, that some ability question of a mixing rule, okay. Um, Okay, this is the equation of state parameter related to activity coefficients. Right? By definition, the gamma is this. Whence this is the gamma here, so we can relate this gamma into this equation here, and then we fill it up here. Okay, right? So this is a Q. We'll live into this form, and Q is actually the summation of all the species. Ki, okay, right? The fraction here. Okay, extrapolations of data to higher temperature. Okay, most of the data are set, at a much lower temperature. But if you want to get the data at much higher temperature, you will require a massive experiment. So what we can do is that we can estimate, through extrapolation from a graph. Okay, we can return it with this GE, this form here, and we expand it, but we know that enthalpy is equal to this equation here, and then we expand this equation here until we got this, okay. GE x1, x2 RT ln gamma 1 and to the infinity. Remember this when we do the line, right? The ln, right? For gamma 1 and gamma 2, it will not reach the axis, so we use the straight line, right? Until with the straight line touching the axis, right? Then we know that's the value, right? For ln in gamma 1 and gamma 2. Remember the two line connecting. Okay, right? With that data that we got, right? So we can estimate. Okay, so in another form here, this is the diagram of ethanol and water. Okay, okay. Initially, this the dot are the data, okay, not from the experiments, and the line are from our equations. Okay, so from this we can use the equation to find what data is it. Okay, so this is look very good. Okay, so one of the reason we do this is so that we can save money because it is very expensive to create to start experimental, cannot those massive experimental. Okay, equilibrium and stability. Okay, the equilibrium state of a closed system is the state for which total Gibbs energy is a minimum with respect to all possible changes at the given T and P. Okay, so we know that for Gibbs energy when it equilibriums, the total Gibbs energy at constant temperature and pressure should be equal to zero or less than equal to zero, right? Because as you can know that the direction of going one direction to another directions are the same. So toward the end it should be zero. Okay, right? Okay. Okay, this is already been I told you already. You can read this. Okay, right. So the G total is actually we can assume it to be equal to the number of mole of the total G, right? Then this should be less than the summation of all the number of mole of G here. Okay, right? From which G is should be less than this, and then we got this expression here. Then it should be less than zero. Okay. Okay, right. So this is the graph that shows the emissivity. Okay? Emissivity means that it makes very well. Okay, right? But somehow, if you notice that over this line here, alpha and beta here, this is emissivity. So it means that uh, either one of the phases are in different form. Okay, right? So this gives a bit curve here. Okay, right? And then we see that delta G here is always negative because right? Where is it? Hold on. Okay, that. Okay, that. The Gibbs energy change of Macy must always be negative, and a plot of G versus X1 for binary system must appear as shown by one of the curves, okay, right, in 14.12. Okay, so it will be always negative, right? Is it in equilibrium? Okay, equilibrium is stability again. So at constant temperature and pressure, the third G and the first second derivative must be continuous function of x1, and the second derivative must everywhere to be positive. Okay, right? So this is it have to be positive. The second derivative, right, for T and P here. Okay, and then delta G over RT we can rewrite it into this form plus GE, and hence the equivalent of here. Okay, right? So we second derivative that should be bigger than negative of this value constant T and P. Okay, right? So toward the end, if we derive it again, right? If you read this, okay, right, we found that the change of viscosity to dx1 should be bigger than zero, and also the chemical potential here, right? Mu I over this should be equal to zero also. Okay, right? Okay, liquid equilibriums. For liquid equilibriums, we know that here we have two phases there, liquid phases, alpha and beta. We have seen this before. Then it should be equal to this. X1, or since the viscosity is the same, then we got this. So the gamma for alpha and beta is a function of this. And the same for gamma for beta of this alpha and beta. Okay. And then we can return it and we find that into this form here. Okay, the degree of freedoms you can guys go back and we find it's only n, okay, because there's two faces. Right? 2 minus 2 faces plus n, so it become only n. Right? Okay, and then this is the equation that we can use. Okay, right? This for gamma alpha, gamma beta, and this is the ratio of ln gamma alpha and gamma beta. Okay, right? So we can rewrite that. Okay, right? So when we plotted that T versus X1 here, okay, right? So we will have X1 alpha, the maximum here, and in the x1 beta over there. So the line from UAL here, half of this, right? This is the reach in alpha. Okay, right? Okay, okay. Oh, I'm sorry. Okay, I'm sorry. Like UAL, okay, right? There's a reach in species 2, okay, right? Because it's alpha. And then UVL, the reach in species 1, okay, right? Because it's closest to 1 here. But sometimes we have to, this is the upper temperature, and is the lower temperature here. Okay, within these two, we have two liquid phase. Okay, out of this system here, we might have maybe only one single liquid phase. Okay, but sometimes we also encounter that it have this, okay, right? Okay, right? We only have the upper temperature only, okay, right? And then sometimes it's only at the lower temperature, okay? Okay, guys, this is for the vapor liquid equilibriums, or VLLE. Okay, right? So if we plotted the graph for T versus X1, Y1, okay, right? So we have this kind of shape. Okay, so C that is in a liquid form, right? And then D is in liquid form for reach. Okay, and E is the vapor form. Okay, right? And then this region here, alpha, is a single rich liquid form. Okay, right? For species 2. Okay, right? So denoted by alpha, and this is the mixture in this region here. So this is the bubble point line, and this is the dew point line. Okay, and this region here, this is for the rich species 2 liquid vapor mixture. Okay, right? This is the same. This is the dew point line for species 1, and this is the dew point for the species 1. Okay, right? So this is the mixture of liquid and vapor, and this region here is a vapor phase. Okay, right? So at this point here, okay, right? And the bottom here, this is the liquid. Okay, okay, right? This is a single liquid, all reach, okay, in alpha. Okay, species 2, and then species 1. Okay, and then over down here is a mixture of liquid equilibriums. Okay, right? Okay, so if let's say we have a point here which is in vapor form, a rich vapor form. Okay, right? And we reduce the temperature, we will encounter a a dew point here, right? Some of the initially is a vapor, right? For both, right? Mixture of vapor, right? And then we reduce the temperature, and then reach at this point here, then we will get notice that some of the species form will start to condense, and then we reduce the temperature, and reduce the temperature further, okay, right, down here, okay, right? So we get a mixture of a species 1, okay, right, until become a bubble point where over here is a rich mixture of species 1. Okay, for M here, we reduce, or we'll notice the same thing, can I? The temperature reduced at this point. Okay, we got some of the species 1 start to condense, and then further more and more until it over here. So over here we have a vapor liquid mixture. Okay, right? So this is the line here. Okay, because this is a liquid, this is the vapor line. Okay. So if we increase the temperature, this is what we're going to be seeing. Correct? This is point E until here. Okay, this point M is where this is C, right? The lotus of C, and this is D. Point M here where it meet, right? C and D meet. Okay, this is the critical point. Okay, for the vapor phase, okay, that for point E here, okay, that we will see that, okay, that you will move, okay, that slightly to the left, and if you notice there, right, so at point F here and J here, so we got a something like vague, a line here, okay, so this is the azeotrope, okay, the locus of the azeotrope, okay, right? So the same thing there, right? So this over here, okay, that will be explained, guys. Okay, for pressure versus these compositions, right? So it will be inverse. Okay, it's still the same things, okay, right? So this will be the higher pressure. This is in liquid form, okay, right? And then this is the vapor form, okay, right? This is the uh, species 2 rich, okay, right? This is all rich in liquid. This is a mixture. The species 1 mixture, okay. Okay, for for the equations, okay, right? VLLE is provided by the modified Rod's law expression, right? By using this equation here, so which we denote as the asterisk, okay, star. Okay, I just call it star, and specifically it can be formed into this, okay, right? A, B, C, this equation here for alpha, gamma, and the P separated, okay, right? This is for alpha, is the same, right? This is for the liquid form, okay, for species at B rich, okay, right? And then if the equation are correct, okay, right, we can consider it to be the same type here, right? So in the case here, when alpha equal to 0, okay, right, and this, okay, right, then we got this value here. It's become P saturated, okay, right, for the vapor liquid equilibrium cell. Okay, toward the end, we can find what is the Y star equation using this equation here. Okay, for liquid vapor, okay, right? For this is the binary system for immiscible liquid. For immiscible liquid means that it cannot mix very well. Okay, right? So it's still the same here. So we still have this is the vapors system, yeah, area. This is the liquid. This is the vapor mixture. My point is the liquid, which in species 2, species 1, the region is still the same. Okay, right? If you move it here, then you got the 3 phase there. Okay? This is for the temperature, and that is for the pressure. Okay, right? So vapor liquid equilibriums again. Okay, we can use some for the immiscible systems. Okay, so we can consider to be this equation here. Okay, right? So the fraction should be 1, right? And then P star should be the combination of the two pressure there. Okay, from here we can find what is a y1 star, and then y1 equal to this, and this is the equivalence, and then y2 we can write it into this form here. Okay.
Hello, welcome back. Okay, right. So the next lecture will be, the next topic will be on solid liquid equilibrium, or SLE. Okay, so this is the phase behavior involving the solid and liquid state, and this is also a basis for separation process. It means that you want to extract a solid from the liquid. Okay, especially crystallizations, and like for example sugar crystallization, something like that. Okay. So indeed, a wide variety of binary phase behavior is observed for system exhibiting a solid-solid, solid-liquid, and solid-solid-liquid equilibria. Okay, right? So for the basis of SLE, okay, right, solid-liquid equilibrium, okay, right, we can see that the fugosity for the solutions is this. Okay, right? This is the liquid, and that is the solid. Where the uniformity of T is understood, okay, right, as in equilibrium, the temperature and pressure is uniform. Okay, and then we can modify this and include in the favor of activity coefficients. Okay, this is gamma here into this form here. Okay, we have seen this before. And then where x1, z1 are respectively the mole fraction of species I in the liquid and solid solution. So we can written it in this form here. And then we have C, okay, right? So we have this C here. Can I C or phi? I think it's phi, okay, right? C, I think C, I here. And then where C is the ratio of this. Okay, so with this, we can return it into this form here where the delta enthalpy here is the solid liquid, okay, right? So it is the enthalpy change of melting, okay, or the heat of fusions. And TMI is the melting temperature, freezing point of your species I. Okay, for this, then we have two scenarios, okay, that we consider for phi. Okay, right? The first scenario is that we assume ideal solution behavior of both phases, means that gamma 1 liquid equal to 1 and the solid is equal to 1. Okay, right? So it's a miscibility, okay? For all T and the compositions. And then we assume that, and the second one is the ideal solution behavior for liquid phase, which is gamma I in liquid form is equal to 1, and complete immiscibility. Immiscibility means that it does not dilute, okay, right? So it doesn't mix well. Okay, for these two questions restricted to binary system, I consider for the following. Right? So the first case here, x1 can be written into this form and x4 into this form here, and then we can solve it, right, for both x1 and z1, okay, right? Because of this, okay, right? X2 is 1 minus x1 and z2 is 1 minus z1, okay, right? So we can rewrite this into this form here, with phi1 is this equation here, and then phi2 in this equation there. Okay, right? So when we plotted this, okay, right, we will find that we got these equations, this graph, okay, right, where this is the liquid form, and this is the solid form, and this is the melting point, right? This is the melting line, okay, right? When liquid turns into solid, okay, right? Frozen. I'm sorry, this confused with the word. Freezing curve. I'm sorry. This is the freezing curve, and this is the melting curve. Okay, right? Okay, right? So solid turn into a liquid. Okay, right? So this region here is the mixture. Okay, right? So this, what you should remember, guys. So this looks like it's similar to the Raoult's law. Right? So for the case 2, where the two equilibrium resulting from this, right, x1 and p1, x2, x2. Okay, right? So we know this is a combine become 1, and x1 plus x2 also equal to 1, and the eutectic temperature E. Okay, right? So that is the eutectic where the 3 point occur. Okay, right? So this equation here, we can derive it, apply 14.93. Right? So we got this equation here, and then we got this is x1 here, and then from 14.93 and 14.94 we can get these expressions here, and then we can plot that. Okay, right? And then we got this graph here. So you guys can see that this is a very similar graph that we have seen earlier. Okay, right? So this is the species 1 rich solid liquid mixture, right? And this is all both are solid in this region, and this is liquid, and this is the eutectic point. Okay, right? So this is a species 2 rich mixture. Okay. Okay, for the solid vapor equilibriums, okay, SVE, we can see that some of the solid, it can straight to vaporize into vapor. Okay, this is called sublimation. Okay, as we mentioned, has been studied in the last semester. Okay, right? So how we can relate the two? Then we can, according to this, okay, right? So this is the viscosity for the solid, and this viscosity for the vapor. Okay, right? So in the solid form. And then for pure liquid, then then for the solid viscosity can be estimated by using these equations here. Okay, right? Where Pi is a saturator is the liquid vapor saturation pressure at temperature T, and VLS is the molar volume for the solid. Okay, right? So for the vapor phase, okay, we can return into this form here. Okay, right? Then from there we can find what is Y1, which is this ratio here, and then we can get this new expression, which is F1, right? So this equation, which is reflect the vapor phase non-ideality through viscosity coefficient, saturated viscosity coefficient 1, and this here in the solid form. Okay, that's all solvent form. Okay, right? And then at moderate and high pressure, vapor phase non-ideality become important. Okay, right? And then I'm sorry. For sufficiently low pressure, both effect are negligible. Okay, right? So very low pressure, right? So we can assume that F1 equal to 1. Okay, right? Because saturated, then this is about the same. Okay, right? And then this, right, becomes 0, right? So this power of 1. So exponent of 0 is 1, right? So at moderate high pressure, it becomes important. For very high pressure, even the pointing factor cannot be ignored. Because F1 is generally observed for greater than unity, is sometimes called the enhancement factors. Okay, they lead to solid solubility greater than will become in the absence of this pressure in this effect. Okay, what does it mean here? Okay, right? The pressure will influence, right, the sublimations of the solids, right? So you, if let's say you increase the pressure, what does it mean? Okay, right? So you might prefer to be in the solid form, okay, right? So if you reduce the pressure again, then start to vaporize into the vapor form. Okay. Okay, so for the solid vapor equilibrium SVE, estimation for solid solubility at high pressure, right? Um, Okay, solubility at temperature and pressure above the critical values of the solvent have important implications for supercritical separation processes. Like, for example, extraction of caffeine from coffee bean, right? So caffeine is in liquid form or in vapor form, right? And then the separation of aspartame from heavy petroleum fraction, okay, right? So so for typical solid vapor equilibriums problem, the solid vapor saturation pressure P is very small. Okay, right? So all of these, then we can return it. You know, all this information here, we can return it into this form here, where the activity fugacity coefficient here is that we can estimate approximately to the infinity. Remember the finite dilution. Remember we have the straight line, so it's close to the axis there. Okay, right? And then in equation these P1 saturated and V1 solid are pure species property found in the handbook or estimate from a suitable correlation. So we can estimate these values here. Okay, right? And also for P. Okay, okay, right? So cubic equations of states such as Solve, Reckless and Kwong, okay, right? And Peng-Robinson equation is enough, right, for this kind of calculation. So there are equations that we can relate for this SRK and PR, right, Peng-Robinson's, right, for solid vapor equilibriums. So we can use this equation here and apply, and then we can find what is Q bar here. Okay. Hello guys again. Okay, right. So another topic will be, our next topic will be equilibrium absorptions of gases on solid. Okay, right? So what does it mean by absorption? Absorption is basically when you have a surface, right? A solid surface, and then the molecule, either liquid or vapor, okay, right, or gases, it will stick to the surface. Okay, right? So that is called absorption. With an absorption with an AB, right? The AB is ab, the liquid or the vapor will enter into the matrix of the solids. But for absorption, no, it's only on the surface. Okay, right? So this surface, so for absorption, it depends on the molecular surface, okay, right, of the absorbent. Okay, right? So most of the absorbents they are hollow, okay, right? Hollow or I mean they're sphere, right? The best will be the sphere type, right? Sometimes with the sphere, they also have a hollow. Okay, right? This will increase the surface of the absorptions. Okay, right? So for a very weak electrostatic inductions or dispersions, okay, right? This is called the physical absorptions. Okay, right? So it's not very strong, but for a very strong absorption, it is the quasi-chemical, means that there's a chemical, it's not reactions, but chemical forces, right, holding the reaction there. Okay, I will not talk much on this because I think this will be covered in your reaction class later. But I can tell you that in the absorption here, it depends on the pressure. If the pressure is very low, there will be only one layer, less molecules, fluid molecule, liquid or vapor will stick on the surface. But at very high pressure, then you will have more molecule stick to the surface, or even it can be multi-layer. Multi-layer. If it's a single layer, they call mono-layer, but multi-layer means that you have a few layers there. Okay, right? Okay, this we can model it by using what we have learned earlier, okay, right? So using this function here, PVT functions, and also the spreading pressure functions here, okay, right? With a molar area. And then the degree of freedoms, okay, right, is n plus 1 because for first species, okay, it's only 1, okay, right? So it becomes 2, okay? Okay, right? And then we can use all this equation, you just recall back, you look at it, right, to the end, okay, right? And then we have for absorptions of pure gas. Okay, right? So you can use this equation here, all of these equations, okay, to solve it. And then Write it down. A bit too fast forward, okay, right? Okay, so we can get into this this absorption. Okay, this is for pure gas absorptions. Okay, right? So we can have this equation here, Z, we find Z. Okay, right? I will go straight. I will go straight. Right? And then okay, this is for the mixed gas absorptions. Okay, right? For the Gibbs energy, okay, right? We can substitute the gas phase GI here, so we can use this equation, and this is the chemical potential. Okay, right? Or for the absorbed analysis equation, then we can use this equation. Okay, right, guys? And then for furthermore, we can arrange this. We can find what is F1, which is the ratio of F1 over Fig. And then for this, we can use this equation. Okay. And then the step for following for mixed gas absorptions, you guys can follow this. All right. So you guys can have time and do the reading. For the next section will be on osmotic equilibriums and osmotic pressure. Okay, right? So I will not talk more on this. So basically, it's very much to look at the pressure differences, okay, right? The partial pressure differences between the two components, right? Like in this part here. Okay, right? Over here we have P prime and P. Okay, right? So the pressure is slightly different, so that will allow uh, the osmotic process to be okay. So I will not emphasize it more on this. Okay, right? So I think you guys can read it. Okay, so how this can work and throughout this. Okay, so that's it for my lecture. So if you have any question, please do not hesitate to ask me. Okay, so thank you very much and have a nice day.